Hey everyone, Dave here, and in this video I will go over the 7-step model that you can apply to successfully complete your data science projects. This model is often referred to as the data science lifecycle, and I will explain why it's important to understand. Now, data science projects are complex and they involve many steps. The data science lifecycle can help you to structure your projects and provide clarity, because by knowing in which step of the lifecycle you are, you can determine the next actions that you have to focus on. And this is especially helpful for people that are just starting out with data science, as it can be very hard to apply all the concepts that you've learned in a structured way. The data science lifecycle can also help you to give you the confidence you need to start taking on projects, because by knowing this lifecycle, you know from a bird's eye view all the steps that are necessary to complete a project successfully. Now, every data science project and every data science team is different, and therefore each specific data science lifecycle will also be different. However, most data science projects tend to flow through the same general steps. I will explain the data science lifecycle with a real-world example from a drinking water production company that wants to prevent water leakage from its pipes using machine learning. I will now first introduce the example to you, and then we'll use that example to go over the 7 steps of the data science lifecycle. Now, imagine the case study over here from a drinking water production company that wants to prevent water leakage from its pipes by detecting bursts early. So drinking water companies have can have several water treatment plants where they treat the water. Basically, raw water comes in, they treat it, and then they turn it into drinking water. And then through a network of pipes that are underground, they distribute it to the households. So when you turn on the tap or jump into the shower, you have nice and fresh water. Now, of course, these pipes are underground, you don't see them. And what can happen is that a burst appears in one of the pipes, which results in water leakage. And of course, this is not something you want as a water company, because this is your product, and basically through a burst, through a leak, you lose some of that product, i.e. you lose revenue. So this is something you want to prevent, and a perfect example of how you can apply machine learning to solve a problem. So imagine the situation over here where we have a pipe with an IoT sensor that pushes data to the cloud. The data comes in real time, and we have a very typical pattern of low levels of flow of water during the night, and then a peak in the morning and another peak in the evening. And this behavior repeats itself every day. It's a very typical pattern. And then when a burst appears, there is a change within this pattern. So for example, over here, you can see some abnormal flow of data. And by the way, this is a graph that I took from the research paper over here. And now, of course, implementing such a model and actively monitoring all your pipes is very interesting to a drinking water production company. So therefore, we as data scientists get the assignment to create a model like this, and we will be using this example to explain all the steps within our data science lifecycle. So let's get into it. Okay, so the first step within the data science lifecycle is business understanding. And every data science project has to start with a good business understanding. You have to ask yourself the question, what is the business or enterprise goal? What do we want to achieve with this model? What is the problem exactly? You have to get really clear on that. And to get back to our example of the case study, we want to prevent spillage of water. And how do we do that? By detecting bursts early. So by framing the problem like that, we can think of ways to collect data and model that in such a way that we can achieve that goal. So it's really important to go over questions like this and also discuss these questions with someone from the business, or typically the person that has given the assignment to you to look into this problem, and really try and understand what their problem is and how data science machine learning can help them to solve their problem. And a conclusion from this step within the data science lifecycle could also be that for the problem at hand, data science or machine learning is not the right approach. It could be much simpler. It could be applying some business logic, for example, or maybe there isn't even any data that we can work with. And that's why it's really fundamental to get a really good idea of the problem that we're dealing with, so we can use the right tool for the right problem. And maybe that is data science and machine learning, maybe it is not. So the main objectives of the business understanding phase of the data science lifecycle can be summarized as follows. So we really define the problem and the goal of the project. And we do this by asking a lot of questions. We formulate a research question, and also we formulate hypotheses. And we also ask ourselves if data science, machine learning is the right approach to solve this problem and achieve this goal. If we decide that data science is the right approach, the right way to solve this problem, then we go on to the next step, and that is data understanding. So next to understanding the business problem, we also have to really understand the other underlying data that we have and that we can work with. So coming back to the example over here, we have a very simple example where we have a sensor that measures a flow, for example, but could also measure other parameters of the water. So it could also measure the temperature, it could also measure various other quality parameters, but in this case, we really have to look into the flow of the water. So we have to look into the data and then determine, okay, so what are the relevant parameters that we have to look at? Are they available? What data sources do we need? Do we have to combine different data sources? The more complex a data science problem is, also the more data you could use and could merge. And as the data set that you're using and the parameters that you're using grows, this data understanding becomes more and more important. In this case, it's quite straightforward. We have a flow, and if something changes within that behavior, within that pattern, something's wrong. But of course, this can be much more complex. We could have tens, hundreds, even thousands of data points, different data points, parameters that we can look into. And we have to understand as data scientists what each of those parameters mean, how they interact with each other, what we can extract from them. So this can become very complex real quick. And this is also why it's very important to be very curious as a data scientist and ask a lot of questions to really understand the data and how you can use that to solve the problem. So you really have to go and talk to the engineers that know how these pipes works and know how water flows through these pipes in order to get a good understanding of why we're seeing these patterns within the data and what is normal behavior and what is abnormal behavior. The typical steps that you perform during the data understanding phase of this life cycle are the following. So we determine the data sources, we describe the data, we check all the data types, we determine whether the data is relevant, and we use graphical plots to get a better understanding of the data. And that brings us to the third step, which is data preparation. So we now have a good understanding of the problem. We know what data we have and what we can use, and we understand the data. And now we have to prepare the data in such a way that a model can understand the data and work with it to solve our specific problem. So typical things that we do within this phase are, for example, let me copy this. We determine if we have to combine different data sources and merge them into a single data set, a single data frame, for example. So we combine data sources. We also check whether there are any missing values within the data and potentially do some imputation of those missing values. So this sensor, for example, might shut down or temporarily doesn't work as intended due to connectivity problems, for example, and that results in a gap within that data. Now, depending on how big that gap is and the data itself, we as data scientists can use various imputation methods to fill up those holes in order to still use that data. But of course, this really depends on the problem at hand. But this is something you do in the data preparation phase. So we deal with missing values, and we also check the data for potential outliers. So for example, for the flow, this would be like a negative flow. If there is a negative value, you know that would be an error from the sensor itself. So that is dealing with outliers. Let me put it up here. So dealing with outliers. What else we got? We have aggregation over here. So we can aggregate the data in different ways. This could be, for example, if you're dealing with time series data measured every minute, for example, you could say, hey, we want to aggregate this data to hourly data in order to reduce the total amount of data. So then you take the average of 60 minutes, for example, and then turn 60 observations into one observation of the data. So that is data aggregation, also something part of the data preparation step, and also feature engineering. So this is creating additional features based on already existing or measured data. Here we typically also define a train and a test split. So we split our data set based on our observations that we want to give to the model, and another set of observations that we explicitly want to keep away from the model so that we can later evaluate the model based on unseen observations of that data. And now there are many more things that you can do within the data preparation step, but I think this gives a brief overview of the steps that you have to take within this data preparation phase. Basically, the main objective of this phase is to prepare the data in such a way that we can feed it into our models. And that brings us to the fourth step of the data science lifecycle, and that is exploratory data analysis. And this is the phase where we get an even better understanding of the data and how the different features relate and correlate with each other by making visual graphs, plots, bar charts, etc., calculating correlations and visualizing those in a heat map, for example. And we already start to get a sense of what parameters, what features have some predictive power for the target variable that we want to predict in the end. So basically, what variables are useful and what variables are not useful. And by doing this, we get an even better understanding of the data. So coming back to our example, in this case, we would be really looking at the flow graph visualized over here. So we will get a visual representation of how that parameter behaves and works throughout the year, throughout different time periods. And additionally, if we have other data, we plot that as well and we check the correlations between those parameters and variables. So we really get creative here and start to explore the data. So to summarize, we create plots and figures. And for example, we create the scatter plots for correlations. And we can also create heat maps. And we can also have a look at data distributions, histograms, stuff like that. And now the next step within the life cycle, the fifth step, is predictive modeling. And now I am recording this clip later because I messed it up, because I went all the way to the last step and then noticed that I was missing a step. And yeah, I messed up. I skipped exploratory data analysis because I was so focused on the process of recording this video and trying to explain everything that I skipped over some of my notes. So in the next clip, you will not see exploratory data analysis, and predictive modeling will be in there, and I'll just continue from there. And then in the end, I will bring it back together. So sorry for that, bit confusing, but I messed up. And this is the phase where we really start to experiment with the different machine learning models that are out there and try and come up with a model that best solves the problem at hand. Now for this phase, it is essential to determine what kind of problem or machine learning problem we are dealing with. So is it a regression problem? and that is a problem where the output of the model is a numerical value? Or is it a classification problem where the output is a label, for example? Or it could also be a time series forecasting problem, which is the case in our example. And this is actually a very interesting example over here, because this is an anomaly detection problem. And depending on the approach you want to take, it can either be a regression, classification, or a time series forecasting problem. So this is actually quite interesting, because what we are looking at over here is a numerical value. So we have a flow over time. So we have a timestamp and we have a flow. And we could, for example, try to model the flow based on the time. And then we can turn it into a regression problem. And then what we can do, we can use the regression model to predict what the flow would be during that time of the day. And then, for example, say if the difference between what the model calculated and what the sensor measured is too big, so the difference is too big, we trigger an alarm. So that would turn it into a regression problem. And you could also say it's a classification problem, because the end goal of the model is to predict whether there is a burst or there is not a burst. So basically 0 or a 1. 0, not a burst, 1, a burst. So that would be classification. But we could also frame it as a time series forecasting problem, where we basically follow the line of the flow and then predict a certain steps ahead into the future, and then use the same approach of comparing the results from the model compared to what the sensor measured, and then also putting some confidence intervals around them, some boundaries, and saying, okay, if it exceeds a certain value or a certain difference, we trigger an alarm. So for this seemingly simple problem, we can already see that there are quite a few approaches that we can take. And depending on the approach we take, we have to select different models and even do some different data preparation steps in order to transform the data in such a way that it's useful for the model. So, predictive modeling. Main objectives are the following. So we define what kind of machine learning problem we're dealing with. So I would say define the machine learning task. And based on that task, we define a selection of models that we want to try. And this is also the phase where we train our models, often with historical batch data. So this would mean looking at all the historical data that we have. So this is only data from 2 weeks, but say, for example, the sensor has already been there for 2 years. Then we take that whole data set of 2 years, which is a batch of data, and then we use that to feed into the model. And ideally, we also have it labeled with a burst that happened in the past. So for example, this abnormal flow of data caused by a burst over here in the data is labeled so that we know, okay, this is a pattern that we want to identify with our model. So that turns it into a supervised learning problem. And I forgot to mention that just here, that it could also be the case that it's an unsupervised learning problem, so that we don't have any labeled training data and we use a technique like clustering, for example, to solve our problem. Another task that we typically perform here is hyperparameter tuning. And this is the process of tweaking the hyperparameters of a model in order to improve the performance. And hyperparameter tuning is also something you do in the next step, which we will get into in a bit. But for now, this basically sums up the predictive modeling part. So this is where you actually get hands-on with machine learning and try and experiment with different models and your data and see what kind of scores, what kind of metrics you can achieve. And talking about metrics, that brings us to the next phase, which is model evaluation. And in the model evaluation part of the data science lifecycle, we test our models with the unseen test data that we separated from the training data during the data preparation phase. So as explained, you of course want to train your model with a set of data and then evaluate it with a set of unseen data. Otherwise, it would be unfair and the model would probably perform really well. So next to running the models with the test data, we also evaluate all the metrics over here. And depending on what kind of machine learning problem we're dealing with, we look into different metrics on which we can compare the models. So for regression, this would be mean squared error, for example, or we look at the R2 score. And for classification, this could be something like accuracy, or we look at the area under the curve, for example. So this is really where we evaluate all the things that we did during the predictive modeling phase to eventually come up with the best model. So typical tasks that we perform here, as mentioned, are evaluating the model with a test set. We compare the different metrics. And here we also ask the question, is the model actually good enough to have a practical use case? And for this, you really have to understand that a model will never be perfect because it will always be an estimation of the real world phenomena that we're trying to model. But a bad model can still be practical and better than the current situation. So if we look at the situation over here, where initially we don't have a model at all, so we have no idea what's going on with the pipes. And the only way to detect a burst within any of the pipes is to visually inspect all of them, which is basically impossible. Then a model that would predict 1 out of every 100 bursts that would occur, which would be a very bad model, of course, but it's still better than detecting none of the bursts at all. So as you can tell, you really have to come back to the business understanding and the problem of the situation that you're dealing with. And maybe a bad model can achieve better results than the current situation. And it's still practical. So basically the question here is, what is the best model? And is it good enough? And a bad model can really be a great starting point to start out with and continue to develop and improve over time. Now, if the model is good enough, then we can continue to the next phase, which is model deployment. And the goal of this phase is to put the model somewhere that we can actually use it to make predictions for new data. And so this process is called model deployment. So typically this is somewhere on a server or in a cloud platform, for example. And we basically put the model somewhere in place where it can receive the data. So coming back to our example, we have the IoT sensor that is sending, let's say every minute, it is sending measurements to a database or to a data lake, for example. And then what we do is we put the model somewhere in a place and we create a data pipeline that, depending on how often we want to send data to the model, but let's say it's really crucial that we detect leaks, bursts as early as possible, and we send it every minute. So every minute there is coming data in from the sensor and we send it to the model, and then the model gives a prediction of whether it thinks that there is a burst or not. So coming back to the 1-0 example, 0 wouldn't be a burst, 1 would be a burst. Then every minute data comes in, 1 or 0 comes out. Data comes in, 1 or 0 comes out. Then these outputs, these 1s and 0s, we will store these in another data table, for example, and we create some kind of rule. Whereas if there is a 0, nothing's wrong. There's no burst, so there's no need to notify someone. But when there's a 1, we immediately want to notify someone. And this could be through an email or an SMS or even a call, for example. You get the idea. Whenever there's a burst, we want to notify someone as soon as possible. And the model deployment phase is the phase in which we realize this scenario. So what we do during this phase is we deploy the model to a server or cloud platform and make it available for real-time inferencing. And in most large companies, this is a whole separate role. So this is not something a data scientist would typically do, but a data scientist would work together with a software engineer or machine learning engineer or DevOps engineer. Different companies use different names for the roles and responsibilities associated with this step. But this step usually also requires some software engineering skills, network skills, cloud architecture skills. So typically something you work together on. And that was the point where I noticed that I messed up, because there was still one empty box and we completed the data science lifecycle because model deployment is the last step. So I fixed the illustration for you. Exploratory data analysis is now right here at step 4 where it's supposed to be. This also concludes the lifecycle. So to sum up, we have business understanding. We define the problem and the goal. We then understand our data. What are we dealing with? What are the sources? We prepare the data for modeling. Then we explore that data in further detail to really get a good understanding of how the individual parameters affect each other and their correlations with each other and the target variable. Then we get our hands dirty by actually building models. Then we evaluate the model to see what is the best model and also is it good enough. And then the last part, if our model is good enough to be deployed, we deploy our model to a server or a cloud where it can be used for real-time inferencing. And as you can see, the final part to this whole equation is a loop back to business understanding. So that's why it's a life cycle. It doesn't really have a clear start and end, but rather it is a continuous process that you can always improve and iterate on. Coming back to the general idea that a model is never perfect because it is always an estimation of a real-world scenario, that clearly illustrates how we can always improve and tweak a model. We can always add more data, add different data. We can tweak the hyperparameters. We can combine different models together. And that's why this data science lifecycle is a loop. And depending on where you are in the project, this gives you a bird's eye overview of the tasks that you have to focus on for that given step of the project. So as I said, this can give you a lot of clarity and a lot of confidence when you're just starting out with data science. Because as we've discussed, there are a lot of concepts: cleaning, machine learning, cross-validation, outliers. All those terms can really be overwhelming when you are studying them and learning them. And then this life cycle can give you a good structure, a structured way of approaching your data science projects, and also gives you some guidelines on what to search for and what to look up during which phase of your project. Okay, so by now I hope you have a better understanding of what the data science lifecycle is and how you can apply it to your projects. Now, if you want to learn more about working with data, then subscribe to the channel. And also the next step would be to really apply this lifecycle to your next project. And I have a video where I explain how to structure your projects, so the folders and the directories with your scripts, in order to best apply this data science lifecycle. So if you want to learn more about that, go check out that video. I will link it on the screen right now, so go watch that next.